Good morning, students. So this will be the very first session of your online class. So we were discussing about carboxylic acid groups, and I have told you earlier in your offline class we will be moving on to the carboxylic acid group that will be having an OH group. I have told you somebody on last Friday. So the first one among the those kind of carboxyl group is tartaric acid, and the other acids are citric acid and lactic acid that we'll be discussing on later. So this is tartaric acid. It is 2,3-dihydroxybutane, 1,4-dioic acid, and this is the possible structure. So COH, and in other side the H is attached, and here an OH group attachment. The same things happens here. Here we can see that there are two chiral carbons. This is two chiral carbon, chiral or chiral, whatever you can pronounce. So these are two chiral carbons, and where these tartaric acids are present. Tartaric acids are usually present in tamarind, grapes, and berries. You know, tartaric acid gives the sour taste to these kind of fruits like tamarind. We know പുളി മലയാളത്തിൽ പുളി എന്ന് പറയും. പിന്നെ ബെറീസ് എന്ന് പറയുമ്പോൾ ക്രാൻബെറീസ്, മൾബെറീസ്, blackberries, all kind of berries will come under that section. So all of these fruits have some kind of a sour taste. So tartaric acid is the reason behind that sour taste. This tartaric acid is seen as a potassium salt in all these fruits, like all these sour taste fruits. We can see that this tartaric acid is being present as a potassium salt. So how we prepare this tartaric acid from grapes? We will be seeing an isolation from grapes. So first we will be taking the reddish brown crust. So the reddish brown crust of potassium hydrogen tartarate is known as argol. We will be seeing a coloration in that fruit. So that crust is containing of potassium hydrogen tartarate, and this one, the argol, that we will be fermenting, like we will be fermenting grape juice, right? So in that process we will be getting the argol, and this argol is being purified. And it is purified and made to a crystal form. We will be making it to a crystal form, and those crystallized form is known as cream of tartar. I hope you guys can see. Don't stress over the notes what I'm writing, or the notes I keep here. You will be getting the hard copy soon. So it is not that much issue. So what I have told is we will be getting a reddish brown crust of potassium hydrogen tartarate from the fermented grape juice, and that is known as argol. And the fermented thing is colorless, and we will be making cream of tartar from argol. How it is? We will be purifying it and crystallizing the argol, and we will be making cream of tartar. So in the next process we will be making calcium chloride and cream of tartar to be conjoined together, that will be mixed together, and to that we will be acidifying. We will be going for acidification process with dilute H2SO4. In that process calcium sulfate is being obtained. I have told you we will be adding H2SO4 acid. So calcium sulfate is being evolved, that will be filtered out, and the concentrated filtrate is tartaric acid. That is the process where tartaric acid is being obtained. So coming on to the structural properties of tartaric acid, we can see a plus sign here. This indicates that it is dextrorotatory and having a deconfiguration. It is dextrorotatory and having a deconfiguration. What if this was a minus? It will be levorotatory, right? So here you can see the structural differences. So also this tartaric acid appears in a racemic forms. Because I have already told you, tartaric acid contains two chiral carbons. Because of the presence of two chiral carbons, there can be an existence of levo, dextro, racemic, and meso forms of tartaric acid. So we can see all these four forms. So here it is the dextrorotatory form. And next we are moving on to the synthesis of tartaric acid. How will be the process of synthesis? So synthesis, in the sense, the first process for synthesize is hydroxylation of maleic and fumaric acid. fumaric acid. Relation of maleic and fumaric acid. Maleic acid and fumaric acid are a kind of cis and trans form of same acid. So we'll be taking two different form of an acid. So first we are going with maleic acid. This is maleic acid. CH, COH, double bond, CH, COH. This one will be the possible structure for the maleic acid, and we will be treating it with KMnO4 and H2O. In this reaction, we will be getting a meso tartaric acid. This one will be the meso form of tartaric acid. So this is a very simple reaction, nothing to be nothing like a rocket science. You can learn easily. This is maleic acid, and we'll be treating with all these reagents. For hydroxylation reaction, we'll be adding water, and we'll be getting meso tartaric acid. So moving on to the next synthesis. So you can see the structural difference between, the difference between fumaric acid and maleic. This is the maleic acid and this is fumaric acid. No such rocket science, simple. The position of COH and H is changed into opposite. So this one with the maleic acid and this is fumaric acid. Same reaction happens here. We'll be treating with KMnO4 and hydroxylation reaction. We'll be obtaining a racemic forms, like a positive and negative forms. This is nothing but the opposition of the functional group. Like COH is being there, but we can see it is completely altered. Like the positions are completely changed to the opposite directions. So this is the second synthesis. Synthesis from cis-trans forms of acids with aqueous KMnO4 that may give rise to tartaric. Final synthesis from acetylene. Acetylene is a CH triple bond CH. This is the formation of form of acetylene. So in this reaction, we can see that this reaction is a step reaction, or a sequences of reaction arises here. Not like the synthesis from fumaric acid or maleic acid. That was a one-step reaction. Here we can see 4 steps. Okay, so this reaction contains sequences of steps. So in first case, we will be taking ethylene. This is ethylene. Ethylene plus Lindlar's catalyst. We will be adding Lindlar's catalyst, and that may obtain to ethylene. We will get ethylene. So ethylene is being treated with bromine water. This bromine water give rise to ethylene bromide. Simple. Ethylene plus bromide, ethylene bromide, and that may be treated with KCN and H3O plus ions. KCN and H3O plus ions. So that give rise to butane 1,4-dioic acid. Remember, I have told you the name of what? Tartaric acid, dihydroxybutane 1,4-dioic acid. So we have obtained the half portion of that tartaric acid. So on further treatment, we will be getting the oil product. So in next step, we will be treating with bromine water, and that will be giving 2,3-dibromobutane 1,4-dioic acid. This one is being maintained there. Bromine is just being added here. One H is replaced with bromine. That's the only reaction have taken place here. So in the final step, we will be adding silver hydroxide, AgOH, that may give rise to tartaric acid. The bromine is being released and OH is being attached here. In the this is the major product, and in sideways we will be getting silver bromide and some water. So this is the reaction or synthesis of tartaric acid from acetylene. What is this? Ethylene, and ethylene is being treated with Lindlar's catalyst, and that may give rise to ethylene. So this ethylene is being treated with bromine water, that may give rise to ethylene bromide. That is a very simple reaction, and from there we will be treating with KCN and H3O plus ions, and that will be giving butane 1,4-dioic acid. The name is somewhat long, but the compound is very simple, CH2OH, CH2OH. So that will be again treating with bromine water, and it will replace one of the hydrogen and may attach to the CH group, making a space, and this compound on treatment with silver hydroxide giving tartaric acid. That's all. That is a synthesis from acetylene. So these are the 3 syntheses of tartaric acid. These are very important reaction. And you may also be able to write what are the reagents we have been using all these reactions, like KMnO4 hydroxylation reaction, and from acetylene we will be using Lindlar's catalyst, bromine water. Bromine water we will be using on 2 places, and this KCN, AgOH, everything you should be able to write. Don't forget about the reagents we are using in the sequences of or in course of reaction. So moving on to the next property or next thing in about tartaric acid is the physical property. Physical property is like how they appear. So it is colorless. Tartaric acid is colorless and is a crystalline solid. Its form is a crystalline solid and it is readily soluble in water. It is very readily soluble in water, but it is insoluble in organic solvents. Organic solvents like benzene and all. So they are colorless, crystalline solids, readily soluble in water. They are very readily soluble in water and insoluble in organic solvents. Moving on to the next topic, it is a chemical property of tartaric acid. So I have told you in the structure, tartaric acid tartaric acid have COH group and OH group, like 2 COH group and 2 OH group. So this compound may have the properties of both COH group and OH group. What I have said is this tartaric acid will be having the qualities of both these groups and they are known for the some of the actions of these two groups, like that actions like formation of salt. They form salt, like I have told you in tamarind and berries and all, tartaric acid appear as potassium salt. So this is a very important factor or a property of tartaric acid, that it forms it has the property of salt formation. So the next property is esterification and then anhydrous formation, etherification, acylation. These are the other properties like what? Esterification, anhydrous formation, etherification, acylation. So but the thing is, the important one is the salt formation. So salt of tartaric acids are usually important. Salts of tartaric acid is very important. Potassium hydrogen tartaric. I have told you in the introduction section. We have already been naming it as cream of tartar. So this cream of tartar is a very important, chemically important thing, and we have a reaction using cream of tartar, that is a chemical property. So cream of tartar is being we combine or we join it with sodium bicarbonate. We mix it with sodium bicarbonate and that may lead to the production of sodium potassium tartarate. Cream of tartarate is being reacted with sodium bicarbonate and we will be getting sodium potassium tartarate. That is known as Rochelle salt. ROCHELLE. Rochelle salt. So this Rochelle salt is a pretty important thing. Rochelle salt is being treated with CuSO4, copper sulfate. And in the presence of NaOH, Rochelle salt is treated with CuSO4. This may give as a deep blue colored complex. The blue color is because of the copper group. So we will be getting a deep blue colored complex that may be water soluble. That compound is or that complex is water soluble. So this is the all chemical reaction. What happens? Cream of tartar is being reacted with sodium bicarbonate and that may give rise to Rochelle salt. This is a structure of Rochelle salt. This H and K are being replaced and where sodium is being attached. So this is Rochelle salt. Rochelle salt is on treatment with CuSO4 and NaOH may give rise to a deep blue colored complex. This complex is known as Felling's reagent. This is Felling's reagent. You have seen Felling's reagent, right? In the laboratory experiments, you will be adding Felling's reagent as a reagent we use. There are Felling's A and B. So one of them is in a blue color. So that reagent is this one. It is made from tartaric acid, tartarate, from cream of tartar. On further reaction, we will be getting Felling's reagent. So as Felling's reagent, we know about Felling's reagent in our laboratory experiments. It is used for the detection of aldehydes and reducing sugars like glucose. Now we will be using these reagents to find whether there is glucose is present or not, like not only glucose, like all aldehydes and other reducing sugars. So this is the use of Felling's reagent. You know already that thing. And the next chemical property is the treatment of what is this? Cream of tartar. So we will be treating cream of tartar with antimony trioxide. This is antimony trioxide. You know antimony, it is a compound. It is being represented using Sb. So antimony trioxide is being reacted with cream of tartar and we will be getting a compound called tartar emetic. Nothing. There is no rocket science to be learned. A simple reaction. So this is tartar emetic. Tartar emetic is used as a moderant in dye industry. You know you guys have heard about dye industry. So dyeing we will be getting color like in clothes and all, no. So in dyeing industries Tartar ametic is a moderant. We'll be using it as a moderant.